Okay, so in the previous video I was kind of looking for what the symbol for algebraic, the set of all algebraic numbers is, and so it's actually this, so Q with a bar on top of it like this. So the Q is for rational numbers and the bar over it is it just shows it's all the algebraic numbers. So we looked at examples of algebraic numbers. So we showed that Q is algebraic. So where Q is in the rationals. So we can actually write that pretty easily as Q is a subset of this. Okay. We also have that square root of 2 is in the algebraic numbers, and you must have seen the proof that root 2 is not in Q. So we see that it's not in the rationals. So the square root of 2 is not in the rationals. So that means the algebraic numbers so are a larger set. So they contain more elements. So at least more elements than Q. Although its cardinality, you'll find out, or you can look it up. But the cardinality of these two sets actually happen to be the same. They are both countable sets. But we won't worry about that right this moment. But so the Q is in set of algebraic numbers, but there are more algebraic numbers than just the rational numbers. There are things like square root of 2 and other things. So next thing I want to show is that for example, square root of any rational number is algebraic. So it's in Q bar. So this is my new claim. That's a D, but this claim is that this is true. And what's the proof? Well, it's not that hard, is it? I mean, so the proof goes like this. You basically see that you noticed that if x squared minus q, that if you let p equals x squared minus q, then p of square root of q is equal to square root of p squared minus q, and then these cancel and then you get 0. So we've just found a polynomial with rational coefficients such that it has a root that's the square root of p, and then so square root of q, and square root of q is algebraic. So this is proof. So we can just put a little but. Okay. So I hope that made sense. So what we have now is that every rational number is algebraic, and we have that every square root of a rational number is also algebraic. So the next one, okay, so far it might not be, it's not very difficult. So let's like try and take out the difficulty a bit. And this one is, so up till now you're just like sitting back and thinking, okay, this is easy, I can do this. Then you should have a go at this one. It's slightly more difficult. It's not impossible. So let's let A, B, and Q be rational numbers. So A, B, and Q are all rational. So A, B, Q are in the rational numbers. Then show that this combination is in the algebraic numbers. So this is a claim. This is slightly more difficult. And to show the thing we're going up to is we want to eventually be able to show that the sum of two algebraic numbers is algebraic, and that the product of two algebraic numbers is also algebraic. And so first of all, we want to be able to show that. So we'll in the next video, because I don't want to make this video too long. We'll show that this part is algebraic, and then we'll show that a plus square root of q is algebraic, and we can put these two facts together and then get this total thing without that much difficulty. Okay, so in fact we only need this fact, because what we can do is we can just factor out the b. You can actually factor the b in, maybe, and we actually. So this problem is the same as this problem. If you see, we can actually factor the b into the square root, and then we get this. So in the next video, we will actually try and solve this problem right here. That this we know is algebraic, this we know is algebraic, and we want to check the sum of these two is algebraic. Okay, so in the next video we will see how to do that.